Hi, good evening, everyone. I'm Thurston Elfstrom. I'm the Executive Director of the Montana Natural History Center. Welcome to Glacial Lake Missoula. We're very pleased to present this evening's program, which is part of Cabin Fever Lecture Series, The Other Glacial Lakes in Northern Montana. This lecture is brought to you by our partners at the Glacial Lake Missoula chapter of the Ice Age Floods Institute. Tonight's presenter is no other than Dr. Don Heineman, Professor Emeritus of Geology at University of Montana, and of course, quite famous for co-authoring Roadside Geology of Montana, along with other roadside, Idaho, Washington, I think there's 6 in total. There's a few of them. Now, a few things before we get to the main event this evening. First, please check out our website, montananaturalist.org, as well as our partners' website, glaciallakemissoula.org. That is currently under construction, but please check these websites out for more exciting events and opportunities. Also, we're going to ask, please don't hesitate to ask questions. Use the chat function or the Q&A function in Zoom to ask your questions at any time during Dr. Don's talk. You can do so while using either the chat or ask a question, as I said, and these questions will be addressed right after Don's presentation. So with that, please welcome Dr. Don Heineman.
Thank you very much. The Glacial Lakes Institute program, of course, is interested in things of cold weather. And the Montana Natural History Association has a new air conditioning system complete with cold air. So instead of exposing my bare head, I'm going to wear a hat. Anyway. Oops, I need to do a couple of things here. Okay. So, other glacial lakes in Montana. I'm going to start off with a couple of little tidbits on Glacial Lake Missoula, which I find fascinating. And of course, can I get rid of this? I'm going to drag that off screen. Okay, so the second edition of Roadside Geology of Montana covers much of what I'm going to talk about tonight, and what I'm going to explain is a spin-off from that. Some of it is not in the book, much of it is. So let's go first to the Ice Age, something more than 12,000 years ago. And it covered, whoops. It covered virtually all of Canada and down into the northern states, including about the northern third of Montana. Note that the ice, you probably can't read the numbers here, but the ice is thickest right over Hudson Bay in more or less central Canada. And it spread outward from there, spread southward, actually in all directions outward from there. But the Rocky Mountains are pretty high, a whole lot higher than central Canada. Hudson Bay, of course, is an inlet from the ocean, so it's sea level. Whereas over here in the Cordilleran area and in the Rockies, we've got high mountains in many thousands of feet high. The Rockies in general are the highest range, and they kind of block the spread of the main ice sheet coming from central Canada. So it had its own ice sheet, also spreading outward, but as far as we're concerned, spreading southward or southeastward into northern Idaho. It didn't spread into most of Montana, but we're going to talk about it. So the ages of the ice periods. We have in the Western Mountains, the main glaciation about, at least as far as the maximum was concerned, 136,000 years ago. And it spread over a matter of more than 10,000 years. The younger period there in the Western Mountains, the maximum was about 16,000 years ago. So the glaciation in the Western Mountains had two big events that are of interest to us here. Out on the plains east of the High Rockies, east of our Continental Divide, there are again two glaciations, and they're sort of the same time. Not exactly, because they were operating as separate ice sheets. In the plains, the main glaciation peak was about 126,000 years ago, and the younger glaciation, 123,000. Now down at the bottom of the screen, it says Pleistocene time ice ages roughly 100,000 years apart. That 100,000 is not a perfect number by any means, but it's held for the last at least 1 million years. And that's been determined from the ice cores in Antarctica, where they've gone back more than 800,000 years, and they've been able to actually date the ice. So why 100,000 years? What's so magic about that? As you know, the Earth revolves around the sun, and we get our seasons that way because as the Earth moves, it's tilted in one direction as it goes around the sun, and so then the northern hemisphere is facing the sun for a while, goes around, and then the southern hemisphere is facing the sun. Those are our two main winter-summer seasons. But at the same time, the Earth is not going in a perfectly circular path around the sun. It goes a little bit farther out and then back and it's a little closer, but it takes a long time to do that while it's going around, or if the Earth's going around it. It takes about 100,000 years. So every 100,000 years, we get our ice ages, and that's when the Earth is farthest from the sun. So there you go. And it's held quite well. So getting in a little closer, if we look at, what happened to my cursor? Disappeared. Okay, if we look at the southern edge of the ice, the continental ice sheet over here, east of the Continental Divide, east of the Rocky Mountains here, we see the ice came down into northern Montana, down to about Great Falls, and that varied, of course, depending upon where we were as far as the ice melting or expanding. So Great Falls over to south of Glasgow, and well, let's just say about 1/3 of the way down through the state. The drainage of the landscape prior to the ice ages was to the north and to the east. So in general, the landscape went from, well, we're at 3,200 feet here, and we're on the wrong side of the divide as far as this part is concerned. But let's say 4,000 or more feet here in central Montana, grading down to Hudson Bay at 0 feet, because that's sea level. So overall, the rivers all headed that way. And if we look at one in particular here, which is handy, this blue patch here is the Missouri, our Missouri River, and it's headed north. Actually, it's headed north partly because the Yellowstone hotspot, Snake River Plain is low, but the hotspot is high. That whole ridge there stands pretty high, and all the rivers drain north from there. So Missouri River heading north, right down through Great Falls. Before the ice, it kept going north. actually north and east, and it ended up in Hudson Bay, way over here somewhere beyond that. The Yellowstone River, which we all know about, goes down from northern part of Yellowstone Park here, more or less past Bozeman, Billings. You can sort of make it out if you got good eyes. There's the Yellowstone River, and it went over here into what became Glacial Lake Glendive, and it was heading northeast, and it, of course, the ice blocked the Yellowstone River, backing up Glacial Lake Glendive. Same for all of these lakes along here. They all backed up against the southward moving ice because the drainages were all headed north and they couldn't keep going north. So I'm going to start off in the western part over here. Here's Missoula, and Glacial Lake Missoula centered on us here, of course. It's most of this branching blue area. And up north here, it's a little bit hard to distinguish which part, but this is Glacial Lake Kootenai. And not exactly the same age as Glacial Lake Missoula, but not wildly different. Both the Clark Fork River, when it reached about the Idaho border, was dammed by ice in what's called the Purcell Trench, really big, more or less north-south valley. Up here in Glacial Lake Kootenai, the Kootenai River up here that goes through Libby and up to Troy and so on, it was dammed by the same Purcell Trench glacier, really big glacier. And by big, I mean thousands of feet thick and quite a few miles across. So, let's see. So what would the landscape look like during the ice ages? Well, if you were to look at the western terrain, our western terrain, west of the Continental Divide, lots of peaks and valleys. Ice would have filled all the low ground, of course, but it didn't cover all the high peaks. The peaks that were not covered remained rugged, like these peaks sticking out of the ice of Greenland. And this is only a few years ago. Oops. So what the Purcell Trench looked like. This is a view looking pretty much north. If you know where Bonners Ferry, Idaho is, it's right there on the screen. So it's at the edge of the Purcell Trench. The Kootenai River comes in from the right here, and it flowed into the Purcell Trench. So when the Purcell Trench was full of ice coming down out of British Columbia, it filled that, and it took a while, obviously, to do so, but go back to that. All the high ragged peaks stood above the ice. So what's it look like here? I don't see many ragged peaks here. These were all, I put arrows on a bunch of them. These peaks were all overridden. Come back here. The curve is wandering. Okay, these mountains here are all rounded. They were all covered by ice. But at the end of each of these white arrows, those were all covered by ice. Back in the background, you can just barely make out some higher peaks that are not rounded off. Same way off in the back here. So that means that the ice in the Purcell Trench and the lower end of the Kootenai River here was high enough to cover all these rounded ridges, all these rounded hills. Pretty doggone thick. So that ice coming down out of British Columbia, slowly, obviously, continually flowing down valley, and at the same time melting. It was that thick. What happened to the Kootenai River? Well, it's not going anywhere. It ran into the ice, and that was it. And so its water, which kept flowing, backed up as the ice dam, as it would be called, in the Purcell Trench, kept it from going any farther. So, whoops. So for the Purcell Trench Glacier at Lake Pend Oreille and the Purcell Trench Glacier, if you know where Sandpoint, Idaho is, west of us, that covered all of Sandpoint, and the ice there was about 2,300 feet thick. So that would be a hard thing for anything to break, including the Clark Fork River backed up behind it. Now, ice weighs about 9/10 that of water. So as the water rises, let me go to the next image. As the water rises, if the water gets up to 9/10 of the height of the glacial ice, then the water can start to lift the ice because the weight of the water at that height is the same as the weight of the same thickness of ice over here. So what happens if it gets that high? Well, as you know, your ice cube in your drink, your ice cube floats, the ice begins to float, and water would then begin to seep under the ice. So then the obvious question is it going to break the ice dam? Now remember, that ice dam is what, 5 or 10 miles across? And it's thousands of feet thick. I don't know that it's going to break it. It's going to lift it. And it'll actually lift it fairly readily. And remember that the water in the Clark Fork is clearly warmer than the ice. I guess that's self-apparent. If it weren't warmer, then it would be frozen. So maybe the ice dam for the Clark Fork didn't actually break. Maybe it floated. If it floated, then the water could slide under the ice. And the water is warmer than the ice, so it could actually help melt its own path through. Here's a little tidbit which got my attention some years ago when I was working for the Geological Survey mapping. We're actually mapping rocks, not mapping glaciers, up in the mountains along the Alaska-BC border, basically east of Juneau. And we're literally 100 miles from nowhere. And so we flew by float plane from lake to lake. A week here to work out from one lake, a week from another lake, and so on. So we landed on this little lake, and it's not very big, as you perhaps judge. Here's the shoreline of the lake that we landed on. And it melted a notch in the edge of this glacier. Now the glacier is a whole lot smaller than the glacier backing up Lake Missoula, but nevertheless, it's a very solid glacier. We came back after working on the nearby mountains to find that there wasn't any lake. Well, that's a little embarrassing because our pilot's supposed to come back and pick us up by landing on the lake, which now doesn't exist. Oops. Anyway, here's a tunnel under the ice. And it's kind of obscured here because part of the flank of the glacier no longer supported, collapsed, but it's still quite obviously a tunnel. Clearly, the water in this lake rose high enough that it lifted the glacier a little bit, enough for water to start streaming underneath. And the water is warmer, so the water melted its own tunnel. Fortunately, we had a primitive radio, so we could radio back to base camp and say, okay, plan B. Now, it is possible that some glacial lakes don't drain that way. Here's one that happened, Hubbard Glacier in Alaska in 2002. In this case, the lake backed up by the ice overflowed along the margin of the glacier. And in that case, of course, it's not necessarily lifting the ice, but it'll still melt a notch because, again, the water is warmer than the ice. And it created pretty good flood. So my question then is, did glacial Lake Missoula form by one of either of those mechanisms? You take your choice. My option would be it probably floated the thing and eroded a tunnel, and yeah, it flushed in a big way. Okay, so let's go east of, oh, sorry, not east yet. Let's go up to Glacial Lake Kootenai. Here's Libby, and some of you, I'm sure, have been to Libby in the more or less northwestern corner of Montana. Highway 2, US 2, goes from Kalispell more or less west, up through Libby, and then Troy, and then up into Idaho, the panhandle of Idaho. The Cordilleran ice sheet, this is the mountain ice sheet, near its maximum, came down about to Highway 2. And I want to show what's happened here. I sort of dubbed it in more or less along Highway 2. Its maximum, it was actually, if you can see this faint blue line down here, that's where it came at its maximum. But at some intermediate stage, it was obviously sitting here about right at Highway 2. Along Highway 2, and I don't know whether any of you know the Thompson Lakes, but these are ice marginal lakes. And you can see in pale blue here that they're long finger lakes right parallel to the highway and parallel to where the ice would have been. So the drainage, both from the meltwater coming off the glacier and the north flowing streams coming up against the ice, those became ice margin streams. This is Thompson River down here where I've got these yellow arrows. And so drainage flowed westward through these lakes and then headed south down the Thompson River, which goes right down to Thompson Falls. West of that, the streams drained the other way, not very steep drainage, into the same Thompson River and again down to Thompson Falls. So these are ice marginal lakes. So keep in mind that the ice at this stage is down to about Kalispell and it's way past Libby and obviously covers Troy and such places. So now we're going to look at what happened as the ice moved back farther north. Now the next several maps have actually been well documented. Interestingly, they were documented by U.S. Geological Survey geologists working on the asbestos Superfund site at Libby. And they needed to know where and when the asbestos ended up in various places. Is it actual natural, or did it spread as a result of mining at Libby? So that, long story short, but that's how they came up with all this information, which is of interest to us. So here's the Clark Fork River, and I've just dubbed in the lake crudely. The Purcell Trench, the main Purcell Trench glacier came down here over Sandpoint. So it's a really big, wide glacier. And of course, it spread up into some of the surrounding valleys, including the Clark Fork, because they were fairly low lying. And it did the same thing up north, where the ice coming down the Purcell Trench spread out in the low adjacent valley up the Kootenai River drainage, backing up Lake Kootenai. So same thing, same basic message for the ice dam for Glacial Lake Missoula and the ice dam for Glacial Lake Kootenai. Now remember, a few images back, I showed you a view of the Purcell Trench as it is now, and the rounded mountaintops that ice was some thousands of feet thick. Is that going to break? I don't see how that can easily happen. It might flow around the margins, but it might just plain lift the ice enough to flow underneath and melt a channel way for itself. Here it is at a somewhat later stage. All of this obviously is in the latter stages of the ice age glaciers in this part of the world, because they're gradually melting back. We don't have a record, of course, for earlier stages because the advancing glacier just obliterate everything. So here's Highway 2, US 2, in this black dash line. Libby is right up there. And at that point, the ice was blocking north flowing drainages, which today, these would flow into the Kootenai River to the north, but there's a big glacial moraine here that dammed it, and any ice that was melting farther east went down through the Thompson Lake spillway and down the Thompson River. To the west, it backed up Glacial Lake Kootenai and its predated parts. So let's melt it back still farther. So remember that the drainage here went down that way. If we go, the last image, Libby was still under ice. This image shows Libby now clear of ice, but underwater of Glacial Lake Kootenai. So now, all of this could be construed as Glacial Lake Kootenai. It's called a different lake name here, but it doesn't matter. Basically, Glacial Lake Kootenai. And it drained from Libby over toward Troy and then south. And the nearest low spot I could find was down through Bull Lake. How many of you sitting in the audience here know where Bull Lake is? Not many. You'd have to be roaming around some pretty remote country, but it's south of Troy and it's north of, let's say, Noxon on the Clark Fork. So Glacial Lake Kootenai was a multi-armed thing filling valleys. So actually, Glacial Lake Missoula wasn't wildly different. It also filled some pretty narrow valleys. Still later, now Libby is way beyond the south end of the ice. Troy is now free of ice, but there is still water of Glacial Lake Kootenai filling the Kootenai River Valley to somewhere northwest of Troy. The brownish colors here are a combination of glacial lake sediments and outwash gravels that came down into the edge of the lake, so they dumped their gravels there and permitted us to map them, or permitted these guys to map them. A little later yet, now Libby and Troy are well south of the ice. And again, the brownish parts are areas that used to be Glacial Lake Kootenai. Bonners Ferry is now essentially at the south edge of the ice. And now the lake level is low enough that it doesn't drain down here through Bull Lake. You can see the spillway for the Bull Lake drainage was 2,356 feet. There was a lower one because now we've gotten over into the Purcell Trench, which is lower. Remember, the rivers all drained into the Purcell Trench. And now there's a lower spillway south in the Purcell Trench. They call it the Elmira Spillway because of the tiny little town here. But basically, it spilled across here and down toward Sandpoint and then off to the west. So keep in mind what's happened then is the drainage directions, the drainage channels depended upon where the ice was and where the lowest spot was to get rid of the drainage. And that varied. And in this case, you can see it varied quite widely. Okay, back to a broad view. Rivers draining north. Here's a shaded relief map. The high mountains are in this kind of purplish color. Hudson Bay over here is sea level. So obviously it's downslope in between. Great Falls is not very different in elevation than Missoula. And we're at 3,200 feet. Great Falls is within a few hundred feet of that. So you go from, let's say, 3,200 feet at Great Falls down to sea level in Hudson Bay, and it's downslope. The shaded relief map shows it's a pretty even slope, more or less, out in the plains, not in the west. Pretty even slope, downslope to the north, downslope to the east, and of course, anywhere in between. So over here at Great Falls, the Missouri River in blue went down to Great Falls, and it used to go at one point up to northern Montana before it turned east. In all likelihood, before any of the ice ages, it went downslope and continued going downslope along these rivers, as you can see, are headed toward Hudson Bay. And the same thing for the Yellowstone River. Starts over here, more or less northwestern corner of Wyoming, goes down and east through Billings, and its drainages go on up through here, and it's headed to the same place. Funny thing, water goes down slope. Okay, so for Glacial Lake Kootenai, I should have had this in a little bit earlier, but here's an exposure of the glacial lake sediments capped by gravels northwest of Troy. Exposures aren't very extensive, but the point here is that they stand way up on the hills. And of course, that meant that the lake was that deep whenever that part of the silts were deposited. Okay, now east of the divide again. The rivers all flow down to the north and northeast. So there's Great Falls, Missouri River draining north, and it, before this ice encroached, it went up through Big Sandy, Fort Benton, which you can't read here, Big Sandy, up to Havre, and then it followed the channel more or less eastward. That channel is a pretty good sized valley. It's a couple of 100 feet deep maybe, and it's, well, at least a half a mile across. I don't know whether any of you have seen the Milk River. It's a dippy little channel. There's not much there. And it sort of wanders around its path. It does not look like it could, under any circumstance, erode that valley. And it didn't. So the pre-ice age channel of the Missouri River went up through Great Falls, Big Sandy, Havre, and it went up to northern Montana and then headed east. Before that, as I mentioned, it probably continued northeast way up into Canada. Same thing for the Musselshell River, generally flowing northward. Goes back up through here, up past Glasgow, and it picks up the Missouri up in here. But again, before the ice ages, it undoubtedly kept going north. Yellowstone River, same sort of scheme. Flowing, it was flowing eastward for a long time, back through Billings, and then northeast and up into North Dakota. So how do we know where the ice got to? What's our evidence? Well, ice grinds over the ground underneath it, and if the ice is pretty thick, it freezes into cracks in the ground, but the ice is not going to stop. It just keeps going, so it yanks up chunks of rock. If you stop your car and look at some of these boulders, and these ones are up along Highway 2 in eastern Montana. They're all white. And you look around saying, okay, where'd that come from? And you look at the outcrops in northeastern Montana, they're not like this at all. These are grainy rocks. These are granites and very high temperature metamorphic rocks that don't look anything like the rocks around here or around Highway 2. They came obviously from Canada. The so-called Canadian Shield covers much of, almost all of the eastern half of Canada. And it's all this stuff. It's all granite and very high temperature metamorphic rocks. So you look at this stuff and it's really grainy. It's not fine grained, dark shales and dark sands that you find in Montana. And the dark shales and sands, of course, are much younger. These things are about 2 billion years old, so-called basement rocks. The rocks in eastern Montana are a few 100 million years old. So what the edge of the glacier looks like at the time. This obviously is, I did not take this back in the 12,000 years ago. I'm old, but not that old. So the glacier would have looked very much like this. This is part of the Greenland ice sheet. It's not mountainous. You know, ice tends to flow downslope like water, more or less. And when it gets down to the ocean or down into a lake, it breaks off because the ocean or the lake is warmer and it undercuts the ice, and the ice avalanches into the water. So it would have looked much like this with icebergs and all those good things. So Missouri River at Great Falls. Missouri River is flowing north or northeastward, Great Falls, and it encounters the edge of the ice. So which way is it going to go? Well, it's got to go down somewhere. It'll fill up the depression, obviously. It'll back up in the river. In this case, it'll back up almost as far as Helena at the maximum. And it's not going to go north as it turns out, because this is actually upslope along the edge of the ice, and it ponded here in so-called Glacial Lake Cutbank for a while, but it's a very shallow lake. It's not a very interesting lake. But Glacial Lake Great Falls, that water was something like 500 feet deep. So a pretty good lake. So where did it go? Well, drainage from Glacial Lake Cutbank went along the edge of the ice because, again, the lay of the land is downslope to the northeast. The ice is blocking it going in opposite direction. So the only place the drainage can go is right down along the edge of the ice. Same thing for the Missouri River, which has pretty good flow, obviously, and did then. The flow of the river had to go somewhere, so it went downslope to the east. It went around the Highwood Mountains here, just east of Great Falls, and it continued north here around the Bear Paw Mountains, and this one is called the Bear Paw. So I think the current version is Bear's Paw Mountains. And it went around the north edge of those mountains, south of Havre, continuing along the edge of the ice. So obviously the slope everywhere in here was downslope against the ice. The only place it could go, for the water could go, was down along the ice. And so it did that for as long as the ice remained at that point, and it eroded some valleys. Pretty good sized valleys. Valleys the size of what you would expect for the Missouri River, which obviously can create a pretty good valley. And it continued on downslope. It backed up over here, forming Glacial Lake Musselshell, which is not all that big, Glacial Lake Jordan here, and then continued all the way east to the eastern border of Montana. So Glacial Lake Cut Bank, and I'm not going to say much about it, partly because it's not very interesting. Its elevation was something of the order of 3,900 feet to the top of the water. At times it got deep enough to be 4,050 feet. No shorelines. You know, the terrain out there is pretty doggone flat around Cut Bank for the most part. The edges of the lake have been mapped just by blocks of rock that dropped from icebergs, melting icebergs. So not going to see much of it. Glacial Lake Great Falls, also around 3,900 feet. Great Falls town, 3,330, so difference when the lake was highest, difference was 570 feet. Nice deep lake. And yeah, it spilled over. And at times, apparently, it spilled over catastrophically for the same reasons that we had catastrophic drainage from Glacial Lake Missoula, and presumably from Glacial Lake Kootenai. And I'll leave it up to you whether you believe it floated the ice or went around the edge or whatever. Okay. The silts in Glacial Lake Great Falls. The lake extended up the Missouri River, that is south of Great Falls, all the way up to about 40 miles north of Helena. And here are the specifics for that particular exposure. Just looking across from one of the roads. And the easiest is road number 280. It's not even a state highway, but it's a paved road, 8 miles northwest of Canyon Ferry Dam. The lake at Great Falls was 3,900 feet, so obviously that lake here must have been 3,900 feet. How about shorelines for Glacial Lake Great Falls? Well, there's some hills around Great Falls, especially to the north. And those hills are pretty soft stuff. You know, they're silts, soft sands, mudstones. And so they erode fairly readily. Here we are about 4 miles northeast of Great Falls on US 87. Well, what do we got going here? There's the hill. I've dubbed in ice here, so ignore the ice, but that's where it came up. And the hill came up this way. And obviously there's a notch eroded in it. Basically the same thing over here. So the hill was a normal looking hill, but you can see that there must have been an ice marginal channel eroded in the edge of the hill, and it came around the near edge of the hill and went back out. Now, I don't know whether the water was flowing left or right to the left, but nevertheless, this is a nice marginal stream channel, and it's really obvious. This is probably the best of the ones that I saw, but many of the hills in this vicinity, and just a few miles northeast of Great Falls, they also show this terrace, and some of them show two terraces. But this one shows such a nice ice marginal stream channel. So this is looking southeast. Remember, the ice is off to our north. So in all likelihood, this ice would have come around, and where we're standing here would have been under ice at the time. So the stream flowed at the edge of the ice, came around this edge of the hill, and so on. Easy to see, easy to get to. So Great Falls again. Glacial Lake is this pale pink in this particular image. Here is Fort Benton, Big Sandy, and Havre. The Missouri River, prior to the advance of ice, went straight northeast. And Highway 87 follows it most of the way. The present Missouri River takes off down here after the ice melted, and it had another channel it could go down. But prior to that, the river went up here to Havre, and from there, east down the Milk River. And I don't know whether you know the names of the towns up there. It's not critical, but get over toward Glasgow along Highway 2. When the ice was blocking the path of the Missouri, obviously it couldn't keep going north, it flowed down along the edge of the ice. And remember, the landscape is sloping to the northeast. Rivers are trying to go northeast, they can't. So then they went around the edge of the ice, generally eastward. And so this was the ice age path of the Missouri, headed down to the east, basically. And you can see the arrows show the direction of ice expansion, ice movement. So if the ice is blocking the Missouri here, and the Missouri River then is channeled over through these rocks north of the high woods, those rocks are not very hard. Again, they're shales, soft sands, and so they erode. Here's a view taken by one of the Montana Bureau of Mines geologists some years ago. This valley, that's the ice age channel of the Missouri River. And it's been called Shunk and Sag. The old-time geologists talked about some of these valleys as being sags, and so it's over near the community of Shunkin, which almost doesn't exist anymore, little farm community east of Great Falls. And note that this channel, the overall channel, meanders. So what controls the meander in a big river? You've got a really big river. Well, some of you, I'm sure, have seen Flint Creek over near Phillipsburg. You drive down Highway 1 south of, well, through Phillipsburg, if you wish. And you look down on Flint Creek. It's a nice little stream. People who are fishermen all know it, I'm sure. And it has these really tight meanders across from one meander bend to the next one might be 50 feet, maybe. If you take something the size of the Missouri River, you're going to be able to kink the Missouri River into that? No, of course, can't. And that's what's going on here. Here's the meander bend of the former Missouri River. The whole Missouri River eroded that channel. Now, if you look down into that channel, it's hard to see. Much of this is dry. Parts of the year, you can see little meander bends if you've got good eyes. As far as the present channel is concerned, they don't follow this big meander at all. So small streams have small meanders, big rivers have large meanders. We'll get back to that in a moment. Okay, this is this is actually a satellite view from Google. And here is Shunk and Sag. Great Falls is off screen to the left. And note that it goes through the river, the Ice Age channel of the Missouri, follows this dashed line through these little ponds, which are ephemeral. They don't survive all year. And note that it's a pretty good channel where it runs up against the steeper hills. It actually cut a nice channel, headed on down to the east. For location, Fort Benton is way up here to the north. Actually, Highway 80 is this super fine line I'm sure you can't see. There's the label for Highway 80, and it goes up past the community of Geraldine. So Shunk and Sag, as it's called, is this big meandering, mostly dry river channel. Here's part of Shunk and Sag from the ground. Lost Lake is west of Geraldine. Now, Lost Lake sits out there and it's not fed by anything. The stream up valley is dry. Down valley is dry. This happens to be a low spot in the channel, but you can see that was pretty good channel. That's part of the old Missouri during the Ice Age. Now to look at this aspect a little bit more, here's the Milk River. And Hinsdale and Glasgow. Glasgow, you probably know where that is in north central Montana, up along Highway 2. And actually this faint white line is Highway 2, and it goes up through here. Anyway, that's pretty wide channel. It's hard to judge here how wide, but think of how big the wheat fields and other fields are likely to be. And that's what? More than half a mile across. And note that it doesn't have any sharp bends in it. It wanders a little bit, but that's the old pre-Ice Age channel of the Missouri, before the ice shoved it up, before the ice ran right across all of this. Now, I'm sure you can't see it on this image, but I'm going to show you a blow-up. The faint dark lines in here show a meandering stream, and the same up here, they wiggle all over the place. That's the Milk River. Here is a closer view of part of it. This, I expect you can see. This is the Milk River. Look at these meanders. They have all kinds of corkscrews down in here. They did not erode this whole big valley. And note that these meanders are really tight. You couldn't possibly do that with something the volume of the Missouri River, either before or after the last Ice Age. So this Milk River did not erode this valley. Some other big river did, and it turns out that that other big river was the Missouri River before the last Ice Age. And to look back again at the same map, Missoula over here, the high Rockies, Glacial Lake, Great Falls, backed up against the ice sheet coming from the north. Glacial Lake Mussel Shell backed up against the same ice. The purplish color is just an earlier ice age that came farther south. And the off-white color here is the later ice age that was slightly more restricted. Glacial Lake Jordan went up to Glasgow. The Yellowstone River flowing northeast, it couldn't go anywhere once it got up almost to Sydney, and so it backed up Glacial Lake Glendive. These glacial lakes are not nearly as prominent as Glacial Lake Great Falls, and the level of the glacial lakes indicated here, depending upon who reported it, somewhere between 3,900 and 3,500 feet at maximum. And that's presumably different heights that it held at different times. And after it drained, obviously, it would be lower, and then the ice would close it off again. Glacial Lake Jordan is a bit of a puzzle. Different people, and I don't know anything about Lake Jordan, except that some people say its elevation was 2,300 feet. Others say it was close to 2,000 feet. there's not much good information on Glacial Lake Jordan, and there's even less information on Glacial Lake Glendive, but it was around just over 1,000 feet. So we went from about 3,900 feet here at Great Falls to just over 2,000 feet for Glacial Lake Jordan and Musselshell, down to Glacial Lake Glendive. It looks like it's dropping a lot, but remember how big Montana is. You know, Montana is what, 500 miles wide. So if it goes down by a couple of thousand feet in 400 miles, it's not a big gradient. And that's it. Thank you for listening.
Well, thanks, Don. That is really fascinating science. Great presentation. We're ready and excited to take audience questions. As requested, many of you out there, at some point over 600 folks over 300 folks asked questions. And so we're gonna flip it over to Lynn, who's a member of the Glacial Lake Missoula chapter of Ice Age Floods Institute, to facilitate those questions. Also would ask, please keep them coming. Keep using that chat function and Q&A, and we'll go ahead and flip over to Lynn right now. Thanks, Lynn.
Yeah. Okay, you're on. Am I showing?
Yeah, you're right on there.
Where?
You can just start talking.
Yeah, that would help. Yeah, Don, you answered actually quite a few of these, but we'll, so that'll be quick. You'll be able to go through them pretty easily. One was, how deep was the ice in the Purcell Trench?
Well, I don't even remember the number, but more than 2,000 feet, put it that way. It was a thick, massive ice. And the ice was just sitting there for the most part. It was slowly moving southward along with all of the ice in the ice sheet, but it would be pretty well stuck to the ground. That is until the lakes adjacent to it built up to 9/10, 90% of the height of the ice, in which case they would begin to lift.
And along with that was a question of how did the Purcell Trench form and why is it in such a low spot?
You had to ask that, didn't you? Okay, the short answer is number one, I don't know.
Okay.
Number two, I don't think geologists in general know, but there's pretty good evidence for the Rocky Mountain Trench, which is the same sort of thing, slightly bigger than the Purcell Trench, but parallel to it. The Rocky Mountain Trench is just barely west of the border between British Columbia and Alberta. And it's a gigantic valley. It has the high Rockies on the east, and it has the Selkirks and Purcells on the west. It's a really, really big valley. Controversial as to how it formed. Some people say it's along strike slip faults. There's lateral sliding faults that ground up the rocks, made them soft, and then the glaciers and rivers eroded them down to where we now see them. Other people say, well, yeah, in places that's true. In other places, it has to do with, I don't know how to express this, but it's a bench in the ancient, really deep rocks. And by really deep, I mean 10 miles beneath the surface, you get the really deep basement rocks of Alberta and farther east. And west of that, I hate to get into tectonics, but with collision of continents, for example, coming against the west coast of North America, we added all kinds of addition of, let's call them, oceanic islands, for the lack of a better word. It's as if you had Japan sitting offshore. Japan sits offshore from Asia. if you took Japan, rammed it slowly into the west margin of North America, so that it then became part of North America, the rocks of Japan are different than the rocks of the adjacent continent. That's probably muddied it sufficiently.
Probably. Is it a coincidence that Lake Missoula and Lake Kootenai are blocked at about the same latitude?
The latitude, not really much of a coincidence, because the continental ice sheet came down far enough south that the average weather stayed warm enough that it would melt faster as it came south than it could advance southward. The same thing would be true of the Cordilleran ice sheet in the mountains to the north in British Columbia. So both of them would be moving southward down to a latitude where the weather stayed warm enough that the ice would melt faster than it could advance.
Okay. So along that line, were the Kootenai Falls formed as a result of glaciation and Lake Missoula drainage?
But they formed as a result? No, I don't think so.
Hmm.
Kootenai Falls, as any of you who have been there will know, is made out of really hard mudstones, kind of dark reddish mudstones. And it's actually a fantastic place. If you go there, it's right along Highway 2. And if you do, you should take the time to stop at the parking area, which is about, half a mile by a good trail down to the river. And if you walk down there, you see flat slabs of bedrock, which are the ancient belt sedimentary rocks. And they're full of ripple marks and mud cracks and you name it, perfectly exposed. And you walk right across them. And those rocks are somewhere between 1 and 2 billion years old, perfectly preserved. So how did Kootenai Falls form? Likely because the rocks that the Kootenai River was flowing across, they're pretty horizontal where the trail takes you down there, but the river is dropping faster than the level of the beds in the belt rocks. And at some point, it went over some relatively hard rocks and had to drop. Basically, Niagara Falls sort of thing. A strong layer of rock keeps the river level high, and after a while, the river gets down low enough into somewhat softer rocks, and so it drops. In the case of Kootenai Falls, it's not spectacular as far as a waterfall is concerned, but it's a really spectacular cascade. It drops over a whole series of rocks, of falls that drop, maybe 10 to 15 feet at a time. Really spectacular place.
We are getting kind of a general question, and how do you date all this? How do you know what happened or when the glaciers formed, when they retreated?
Okay, we're looking at times, let's say 12 to 20 or maybe even 60,000 years ago. How do you date those sorts of things? Well, you can date wood. You can date carbon dating with carbon isotopes of wood. That'll take you back more than 40,000 years, at least to 40,000 years. And it is quite accurate dating. You look at, I don't want to get into isotopes. You look at the different isotopes, carbon 40 it's called, and measure the amount of carbon 40 versus carbon 39. And you know how fast that changes because people have measured it with great precision, and you come up with an age. For younger stuff, it gets a little tricky. If you look at, you say, okay, we've got boulders sitting out on the hills along Highway 2, boulders of granite. How long have they been sitting out there? Now that's a good trick. There's no wood. Granites don't contain any wood and never have. So what people most commonly do is they use a different kind of isotope dating. Most common one is to measure, again, it's an isotope. Again, I don't want to get into isotopes, but certain elements have different numbers of electrons, different numbers of atoms, if you wish. And if you measure on the surface of these rocks that have been sitting around for a few thousand years, you can measure the amount of beryllium-10. This doesn't mean anything, I'm sure, to most of you, but beryllium-10 is an isotope that has certain configuration. So all beryllium is still beryllium metal, but it has a certain configuration, and cosmic rays from the sun beating on the surface with that beryllium in it change that to a different isotope. And again, you can measure the amount of beryllium-10 versus the so-called daughter product produced by irradiation of the sun's rays on that. And it works moderately well.
Another one, if Lake Missoula floated the ice and melted a tunnel, would you get enough water to form those channeled scablands?
Good question. Remember the dinky little lake that I went back expecting to get a plane ride out of? That wasn't a very big glacier. It was probably 100 feet thick. The tunnel under it was, what, 25 feet high maybe, in a sort of rounded tunnel. And so if the lake lifted the glacier, floated the whole glacier, it doesn't matter how thick the glacier is, as long as the water gets up to 90% of the height of the glacier, it'll float. So obviously the water will channel itself through, mostly through areas where the water is deepest, and that the water will move faster in those areas, hence the tunnel. And it will erode it, not in the normal sense of scraping it away, but by melting its way. So is it possible to get enough water under the Purcell Trench Glacier in order to form the channel scablands? I don't know the answer to that, but I suspect it could. You know, we're talking about water behind the glacier for Glacial Lake Missoula was, let's say, a couple of thousand feet deep for the sake of discussion. It's lifting the glacier. It's not just lifting it under the inferred tunnel, but it's lifting it over a big area, and the water is going to be going under a big area. It's going to concentrate in a tunnel or tunnels because that's where it creates the largest channel. You could get an awful lot of water under there.
Have there been any fossils associated with glacial lakes in Montana?
Not that I'm aware of. Somebody correct me if they're aware of any fossils. There probably were animals around at the time.
Yeah.
As the lake drained, what do you suppose happened? It would have flushed everything, live ones and dead ones, and bones. So I don't know. Let me add one other thing about water under ice. The water people are doing research in Greenland now, Antarctica as well, but more Greenland. The glaciologists that work in Greenland find streams on the surface of the ice because the ice is melting in the summer, and the stream will wander around the surface of the ice, and then it'll drop directly into the ice, and the ice up there is thousands of feet thick. It goes straight to the bottom of the ice and eventually comes out at the toe of the glacier. even before you float the whole glacier, there's going to be streams under the ice. And those streams are melting the base of the ice. And late in the summer, it's going to be not well attached to the base.
Do some of the other glacial lakes have lake bottom silt deposits similar to those found within the boundaries of Glacial Lake Missoula?
Yeah, I showed you a picture of
You did.
lake silts for Glacial Lake Great Falls. They have not found any in Glacial Lake Cut Bank. I don't think it lasted very long, and there's not much there. For the other glacial lakes, apparently there are a few exposures for Glacial Lake Mussel Shell, for example. Not as extensive as Glacial Lake Great Falls, nor as extensive as Glacial Lake Missoula. The same stuff.
What evidence do you know of early Native American knowledge of the floods?
I'm not an anthropologist,
Okay.
but I know the early Americans supposedly came across the ice bridge up between Alaska and Asia and wandered down this way. They probably did so in the relatively warm periods between the ice advances. But would they have been living along the shores of Glacial Lake Missoula? I would presume they were. So how long between flushing of glacial lakes? Well, not all that long when you think about it. 50 years-ish. So folklore among them must have said, these lakes don't always stay there. The gods did something or other and the water all disappeared within a few days. So might there have been natives paddling around Lake Missoula? I presume there might have been. Do they leave any record? Well, I'll leave that to your imagination.
Okay. Well, which glacial events then created the lakes and ponds of the Blackfoot Indian Reservation?
Yeah, there's controversy as to how those formed. You're talking about the things that we used to call kettles. And kettles used to be, their origin used to be thought of as when the ice melted back at the 12th Glacier, it left some chunks of ice that were thicker or in hollows or whatever, and they didn't melt for a while. And the gravel coming off the glaciers spread around them, buried them, and eventually that ice melted, and so it left a hole in the ground. If you think about that, those ponds up there tend to be pretty doggone round. Most of them, not all of them. Some of them are irregular. You can imagine what would happen if ice was stranded, partly covered by gravel, and then that ice finally melted. I wouldn't think very many of them would be around. And it turns out more recent research suggests that actually those are so-called pingos. And a pingo is a mass of ice that grows in an Arctic environment. And I won't get into the details, but it bulges up rather than being a collapsed structure. And so the sediments you see around the edges look different.
Getting some pretty technical questions here and some are pretty general. How can we use the knowledge of past glaciation and lake outbursts to study present day and future glacial lake outbursts or any other extreme events?
Okay, I mentioned something related to that. Part of it was the little lake dammed by a glacier along the BC-Alaska border, which disappeared within a couple of days. And it might have happened very, very fast. We weren't there. How else do you study them? There's a number of these sorts of sudden glacial outwash lakes draining in various places. And some of them have been quite catastrophic in places like Iceland and in Greenland and so on. And some of those are pretty well known. Beyond that, I don't know what to elaborate on.
Okay, here's someone who says that she's familiar with a drilling crew that drilled just outside Bonner's Ferry. The soils were sandy, as I recall. Were these sands deposited by the ice sheet, or were they carried by a river flowing along the margin of the ice sheet?
Good question. Could be either.
Mhm.
The silts that you find deposited by Glacial Lake Missoula, and that you still see, for example, out at 9 Mile along Interstate 90, the very fine silts were deposited from silt that was suspended in the water. If you look at the big road cut at on I-90 at 9 Mile, you see alternating layers between silts and sands. The sands were deposited by the streams that flowed after the silts were deposited, or before the next layer of silts were deposited. So both are true. I'm sure many of you have been to Glacier Park, many of you have been to other places near glaciers, near active glaciers. And if you are close to the glacier, the water is very milky, light milky green. As you get farther downstream, the water turns darker and darker because there is less and less silt suspended in the water. So either could be true. It could be, if it's really sandy stuff up by Bonner's Ferry that you're referring to, likely that was deposited from streams. You're not going to suspend sand in water very long.
The comment on Lost Lake near Shonkin having no inflow or outflow must mean that it's fed by a spring? Would you guess that?
Depending upon your vision of a spring, yes. Basically, almost all lakes are the top of the groundwater level, the level of water standing in the ground under it. There's water standing in the ground under our feet in Missoula. If you dig a deep hole, obviously you eventually get down to where water would be standing in it. If it is a natural hole, then you would call it a lake. So a lake is the top of the water table, the top of the water standing in the ground naturally. Streams are also the top of the water table. The Clark Fork River running through Missoula, the water doesn't all come from Phillipsburg or somewhere far upstream. The water, to a large extent, comes from the ground under our feet. It seeps into the stream. So both lakes and streams are the top of the water in the ground.
We've got a couple more technical questions and then just a couple fun questions. If a river can incise a mountain as they rise, why would it not do the same to an approaching glacier? If the river was warmer than the glacier and could melt the ice, creating conduits, then why would it need to float it? Wouldn't the stream channel already be there?
I'm not entirely sure I understand the question.
Yeah, me neither.
But the photo that I showed of that little lake up in the coast mountains that drained more or less overnight. The top surface of the lake was well marked by a notch, a very horizontal notch, obviously. That notch was melted into the edge of the glacier because the water was somewhat warmer than the ice, just because the water stood there for a while. Maybe that's part of the question. I'm not sure of the other part.
Yeah. We've had some questions that I believe you've already answered. Did the route of the Missouri change due to the advance of the glacier? And I believe you answered that.
Yeah, certainly. And the other thing related to that is, you know, the glacier was always moving. The toe of the glacier, that is the southern edge of the glacier, did not stand at one point. It depended upon how much snow was being added to the glacier up the slope. Therefore, how fast was the glacier moving downslope? How fast was the toe of the glacier melting back at the same time, depending upon the weather? And so the edge of the ice sheet would have been varying all the time. So did Glacial Lake Great Falls fail catastrophically? Apparently it did, probably several times. How many, I don't think anybody knows, but it would depend upon the ice coming down, blocking the outflow channel for a while until the lake level could get high enough that that would fail one way or another.
What happens to all the sediment from the lakes and the valleys?
It went downriver.
Okay.
Sorry to be flippant, but I don't
Are
know
there-
the details, but they obviously went a long ways down the river. Some of it would have gone all the way down the Missouri and into the Mississippi and ultimately to the Gulf of Mexico, because those existed at the time too.
Okay. Are there other wildly meandering rivers like the Milk that are probably also remnants of much larger age streams?
Yes.
Okay. We are just about there.
Just keep your eyes open when you're driving around areas that were once covered by ice. And along Highway 2, in places along Highway 200 in eastern Montana, you can see places that little stream, there's no way it could have eroded that big valley.
We'll get to a couple general questions now. When are we due for another ice age to counter the mess we are in with climate change?
Okay, remember the main ice ages come along approximately every 100,000 years. The last one was what, 15 or 20,000 years, 10, 15, 20,000 years ago. So we've got a while to go. There are other influences that would affect it. That is, the ice ages don't come along exactly at precisely the same time. There are blips in between. It gets cold or warm at times, not like an ice age, but there are other wobbles that the Earth does. I talked about the Earth getting farther from the sun and closer to the sun. Farther from the sun, finally get it cold enough, it's in an ice age. But the Earth also does a few other things. It wobbles like a child's top, slowly. It gradually tilts on its axis and back, and does that back and forth very slowly. The intervals for those changes are, for example, one of them is 40,000 years. So, and the ones that we know about are fairly lengthy. If you want to read about these and the influences, Google what's called Milankovitch cycles, Milankovic. pH or something like that. And a lot has been done on that, and that really does nail down what's happening with our long-term climates.
Hmm. Why do you think glacial Lake Great Falls flowed north around the Bear Paw Mountains rather than east from Lost Lake down to the present-day Arrow Creek and onto the present-day Missouri?
Good question. I would have to look at a detailed topographic map to see which is the downslope direction. But remember, even though it might be downslope down Arrow Creek, as it presumably would be, the Arrow Creek exists and still exists, but as soon as something would block the upper reaches of that, some part of the ice would block the upper reaches of that, that's going to channel the water in some different direction. And it's going to probably happen quite a few times, because you can imagine that the ice is flowing southward, not very fast, is melting back northward, not very fast. But what happens over 1,000 or 2 or 3 years? There's going to be a lot of this back and forth and a lot of changes in the channel. So what we've mapped as the main channel for Ice Age channel, for the Ice Ages, path of the Missouri, is where it rested for quite a while. And once it eroded down to a relatively deep valley, that was a pretty good exit for the water.
You know, I guess they're ready to lock up around here, so we'll have to call this done.
Okay, thank you.
Yeah, thank you.
Okay, just a quick word to close up. I'm Jim Sheldon. I represent the Ice Age Floods Institute here in Missoula. We hope you had a good evening, learned some good stuff, at least some stuff to talk about and argue about. This is recorded and will be available on the YouTube channel for the Natural History Center. It's also recorded on MCAT and will be available there. So with that, we'll let you get back to your evening. And thank you all for attending. If you liked it, let us know. If we can make these better, let us know. Thank you.